So we have already understood what it means by centripetal acceleration and centrifugal acceleration and the corresponding forces. We already know what those actually mean physically. Now let us try to derive the very common formula that we see for centripetal acceleration, which is equal to v squared by r. So let us see how that formula actually comes. See, centripetal acceleration is equal to v squared by r. Therefore, if the body had a mass m, the centripetal force will be equal to m v squared upon r. Okay, that is very simple. It should not come as a surprise. Now let us try to derive this formula. So for this, we will draw a body which is actually moving in a uniform circular motion, and for that I have used my special pen here, or a special circle here to draw that body. So this body is moving in a uniform circular motion, and of course there is a center C. You can imagine it to be a stone which is tied to a string, for example, and there are the two positions of this body. So this is the first position, okay? This is the initial position, that is where it starts from, and this is the final position, this is where it ends up being. So we will consider everything which is happening between these two positions. So let us say, so one of the things which will clear right off the bat, right in the beginning, is that the velocities in these two positions, see, velocity here would be like this. It would of course be going, the body would be trying to fly away from the circle, and that would be the direction of velocity. It would be tangent to this circle, and the velocity right here would be like this again, which is tangent to the circle. So that is those are the two velocity vectors. We'll call them v. The magnitude remains the same. Of course, the direction changes. That is the thing, that the direction of this velocity is changing, and that is the cause of our acceleration, the centripetal acceleration that we are discussing now. See, the centripetal acceleration can be provided by any kind of force. It could be provided by gravitational force in the case of Earth and Sun, or Earth and Moon. It could be provided by electrostatic forces in the case of atoms and electrons and protons, right? Or it could be the tension in the string when we are rotating a stone in our hand. So it could be anything. But in each of these cases, no matter where the force comes from, the magnitude of this centripetal acceleration should be equal to v squared by r. That is what we are saying. We are making a general statement. If the body is moving in a uniform circular motion, if the velocity v is not really changing. So in this case, the velocity v is not really changing. Only the vector, the direction is changing. And of course, these two vectors have the same magnitude v, but they are different direction. And what is the angle that has been covered in this time t? So this is the time equal to 0, and this is the time equal to t. So in this time t, what is the angle that has been covered? Let's say that it is equal to theta. So the body has moved an angle theta in time t from this initial position. So this is our initial position, we'll just call it I, and this is our final position, we'll just call it f. I'll just redraw these two vectors, the velocity vectors right here. Nothing special, I'm just redrawing it, these two vectors. So this is my first vector. I'll just draw it a little longer so that things are a little bit clearer. And this is my second vector. So this second vector actually, oh sorry, wrong direction. So this second vector is equal to this is the initial vector and this is the final vector. So if I take the difference between these two, it will come out like this. Okay, that is very clear. So the magnitude of both of these is same, magnitude is v, and this is the direction. The direction is different, and this is the difference between these two vectors. So this is the initial vector and this is the final vector. Now, one of the things that you will notice is that there are two triangles which are formed here. So we will just join these two lines as well. Okay. So there are two triangles which are formed here. One is this triangle, which we will call A, B, C, and this is the second triangle which we will call A dash, B dash and C dash. And if you think about it, if this angle is theta, this angle also has to be theta. Why is that the case? Because the velocity vector is tangent to the circle. This is the radius at the point of tangency. So this angle has to be 90 degrees. Similarly, this angle also has to be 90 degrees. And because the velocity vectors are both 90 degrees to the corresponding radius vectors. If the radius vectors are making an angle theta, the velocity vectors also have to make the same angle theta. Because of this isosceles triangle VV with an angle theta between it, this isosceles triangle, we'll just call the radius R. RR with a theta between them have become similar triangles. Okay. So this is the similar triangle. These two triangles are similar. A dash, B dash, C dash and ABC are actually similar triangles. And one of the properties of the similar triangle that you would have studied is actually very simple, that the ratio of corresponding sides is the same. So what we are saying is AC by A dash C dash is equal to BC by B dash C dash. Okay, so these are just magnitudes. Okay, we are not considering any kind of directions for now. We are just saying that these are magnitudes. Nothing complicated, very simple. Now let us focus on this triangle and the side B dash C dash first. This we said was the B dash C dash, the vector B dash C dash is actually the change in velocity vector. Okay, so this vector represents delta V. It represents the change in velocity from initial to final, from initial velocity to final velocity. That is what this B dash C dash is representing. It is the subtraction of these two vectors, difference of these two vectors. And we know that what is the change in velocity? If the acceleration A is happening for time t, then this is what the change in velocity delta V would be, because the body is accelerating at an acceleration of A, which in this case is our centripetal acceleration. That is the okay, so that is the centripetal acceleration A, and this is centripetal acceleration is happening for time t, and this is what has resulted in the change in velocity delta V or B dash C dash. So now we can fill in some values here. So first we'll fill in AC. AC is equal to R, A dash C dash is equal to V, and here we don't really know BC, we'll get to it in a minute, but we definitely now know B dash C dash, and the magnitude of it is equal to 80. So we are only concerned with magnitudes here. Okay, that is what I have been saying. This B dash C dash is actually the change in velocity which has happened over time t, and that is equal to acceleration into time 80. Okay, so this is what we have filled. Now let's focus on BC. See, as this theta becomes very small, as this theta tends to 0, you will notice one thing, that this arc BC, the arc BC will become equal to the side BC. Okay, there is a difference between those two. Okay, notice there is a difference. So we'll just highlight the difference just so that it is clear. This is the difference between these two. Okay, so this is the arc of the circle BC. This is what we have drawn here, arc BC, and this is the side BC. This is our side, this right here, the one below. Okay, this is our side BC, the side of the triangle. Here we have the side BC, not arc BC. But this arc BC has a special property. What is this? Arc BC is actually the distance covered by this particular particle in time t, which is equal to what? So if we draw this, arc BC is the distance traveled by this particle in time t, which is equal to its velocity into time. It is the very definition of distance. In the limiting case, when theta tends to 0, as this theta becomes very small, arc BC becomes equal to BC. They really become the same, and this is why our BC, we can write it as VT. Oh. This of course is true only in the limiting case when the arc is very small. But of course we are not really concerned about that limiting case, because in the sense that, let us consider that special case. Our formula, if it is derived there, then it will be valid at other points as well. Okay, so now we know that this length BC in the limiting case, okay, so this is the limiting case, as theta tends to 0, as it becomes 0, will be equal to Vt. So let's just write it right here. This T and T would cancel, this A would really go there, and this will become V squared by R. Okay, And this is the derivation. Okay, very, very simple. You can expect questions based on this, and notice that this is the centripetal derivation for centripetal acceleration. That acceleration can come from a variety of forces. I told you this again and again, but the value of that acceleration in the case of uniform circular motion always remains the same, which is the square of velocity into r. And if you want to express this in the terms of omega, which is our angular velocity, then this becomes omega squared r. Okay. And the r actually comes to the top, and this is because of the relation between the v and omega, which we'll study in a subsequent class. So hopefully this aspect is very, very clear. There is a simpler way to understand this thing, more intuitive way. If the body is rotating in one cycle, it will cover a distance equal to 2 pi r. That is the distance covered in one cycle. And the change in velocity, the net change in velocity, because the velocity vector has rotated by a full angle of 2 pi, the net change in velocity is equal to 2 pi r. Okay, so this is a very rough definition, mind it. This is not the total change in the velocity vector is 2 pi v. This is the total change which the velocity vector of v has accumulated. Again, we have converted this vectors r and v into some kind of scalar quantities. Okay, but this is just for our intuitive understanding. This is not an exact definition. The exact definition we have already done. And of course, acceleration is equal to change in velocity. The total change in velocity we are saying is 2 pi v. And what is the elapsed time? This is the total distance which is covered, and it is covered with a velocity of v. Therefore, this is the total change in time which has happened. So it is 2 pi r by v. And of course, 2 pi and 2 pi cancel, and this becomes again equal to v squared by r. Okay, but this is a rough derivation. This is just for our intuitive understanding of where this v squared by r, this acceleration really comes from. The exact definition we have already done, and that is what you should really use. So hopefully these things are clear. Numericals we will be solving based on this channel itself. So do subscribe. If you are having problems on Doorstep Tutor, we have a mechanism where you will be able to submit your doubts, and those also will be covered in subsequent classes on this channel. But you will have to submit your doubts over at doorsteptutor.com. So feel free to do that. Thank you.